Hi, and welcome back to Applied Machine Learning Lecture 3. In Lecture 1, we saw what was machine learning, and we looked at different approaches to machine learning, which included supervised learning, unsupervised learning, and reinforcement learning. And then in Lecture 2, we looked at supervised learning more closely, and we saw what was the structure of a supervised learning problem and what were the components of a supervised learning algorithm. In this lecture, I want to now define our first supervised learning algorithm, which is going to be linear regression. We used linear regression as an example in the previous lecture, but we always used we used an implementation that was created for us already. And in this lecture, we are going to define linear regression from scratch. But before we do that, we are going to need a few tools from the field of optimization. And in this, at the beginning of this lecture, I want to also start by providing a background on certain concepts from calculus and optimization that will be useful for defining the algorithms that we're going to be using in the rest of this lecture. So again, the first part of this lecture is going to be a review of certain important concepts from calculus and how they relate to optimization. Before I begin, I want to again remind you about the structure of a supervised learning task and the structure of a supervised learning algorithm. Essentially, if we want to apply supervised learning to a certain task, we want to first collect a data set, a labeled data set of examples that show certain behavior that we want the algorithm to have. And then we define a learning algorithm that the computer uses in order to extract a signal from this data set and use it to define a predictive model. And the predictive model is something that we can use for useful tasks, such as prediction and other tasks as well. And this learning algorithm, internally, it is also made up of several components. These include the model class, the objective, and the optimizer. The model class is the set of all the possible models that we're going to consider. For example, this could be the set of all linear models, and we're going to look for a predictive model within this model class. The objective is a function that defines a score for how well a certain model in our class is, how well does it fit the data. And an optimizer is an algorithm that chooses a model class which fits the data well according to what our objective is saying. Now, a little bit more formally, the optimizer has the following structure. Here we have defined the function that the optimizer performs a little bit more formally. Here, the optimizer essentially is trying to find the function, the model within within the model class that we're interested in. Again, this could be the set of linear models, and this could be one particular linear model. And it's trying to find the model with the best possible objective value, or in other words, the lowest possible loss value. An example of what J could be is the mean squared error. So for example, the mean squared error would look at the difference between the output of f on an input x and the actual target that we want the model to output. And if the output of the model on the input x is similar to the target y, then we say that the model has a good fit on this training example, and the model will have overall, if this is true for all the training examples, then the model will have a low loss. In this video, we will use as a running example a quadratic function. Here I am defining what a quadratic function is, and in the first cell I am importing the usual libraries that we're going to use, which include NumPy and Matplotlib for visualization. And here I am simply defining a one-dimensional quadratic function, which is a function of a scalar input theta. And here I am taking theta and multiplying it by 2, subtracting 1, and then I'm bringing it to the power of 2, which means that the output of this function will involve a term that's theta taken to the power 2, which is what makes it a quadratic function. we can easily visualize this function, and it looks as follows. Here I've taken a set of values for this a set of thetas, which are I've taken 10 samples of theta within this interval between minus 0.2 and 1, and I've computed the value of the quadratic function at each of these points. And visualizing these values, we obtain this nice blue curve, which has the distinctive shape of a quadratic function. It has a minimum here at around 0.5, and again, it has this smooth rate of change that's characteristic of a quadratic function, as you would expect. Now, in order to start to define the concepts from optimization that we are going to need, we will start by revisiting and mentioning a key concept in calculus that will be necessary for defining the algorithms that we're going to look at, and this is the derivative. If you're not familiar with what is a derivative, I encourage you to review materials on the derivative from a first-year calculus course. But for the purposes of this lecture, you can think of the derivative denoted as follows. This is the derivative of f with respect to its parameter theta evaluated at a point theta sub 0. You can think of this in a few ways. One way of interpreting this value is the slope of the tangent at the point theta 0. So we are looking at the tangent line to the curve f at the point theta 0, and the derivative will equal to the slope of the function at this line. Another way of looking at the derivative is the instantaneous rate of change of the function at the point theta 0. And of course, there are many other ways of looking at derivatives. There is a formal definition, but for the purposes of understanding these algorithms, we are going to stick with this intuition. To make it a little bit more concrete, here I'm going to plot a few derivatives for the quadratic function. First, I'm defining a function that outputs the derivative at any point theta. Here, this is just the expression for the derivative that I obtained using standard rules in calculus. And now I am computing the derivative at the value of when theta equals to 0. I'm also outputting here the value of the function at theta equals 0. And here in this line, I'm visualizing the derivative, and it happens to be exactly the slope of the tangent line and of the line that's tangent to the curve at the point theta equals 0. And also, in other words, this is also the instantaneous rate of change of the function at this point. So again, this matches the intuition that we saw earlier. Here I'm going to plot a few more derivatives. Again, these are all the tangents. These correspond to the slopes of the tangents of this curve. And here I have also shown the derivative at 0.5, which is the minimum of this quadratic function. And you see here that this is a flat line which has a slope of 0. And as you would expect from standard calculus, the slope first of all, the value of the derivative at the minimum of the function equals 0, and this can be seen intuitively as the slope of the tangent, or the rate of change of the function being 0 at the minimum of the function. This is an important fact about the minimum of functions. The fact again being that the derivative of a function at its minimum equals 0. This is an important fact that will be useful later on, and again, I would encourage you to review this concept from a first-year calculus course if you feel like you need a little bit more intuition and understanding of as to why this is. Now, the functions that we are going to consider in this lecture are going to be more complicated than the quadratic function that you just saw. We are going to be working with quadratic functions we're going to be working with functions of many variables, and the input to these functions is going to be a d-dimensional vector for some arbitrary dimension d. And the extension of a derivative to these multivariate functions or one possible extension, is called the partial derivative, denoted as follows. Again, you do not need to know the formal definition of this, although it will be useful to fully understand the material that will come later, but it's not strictly necessary. Again, the simple intuitive definition of what a partial derivative is that it is simply the regular derivative of a function of a multivariate function when all the inputs except the jth one are fixed to some arbitrary value that's specified here within theta 0. So so we are going to fix all the other d-1 inputs to f to some value, and we are going to take the derivative of this function with respect to theta j. And that is the intuition about of what is a partial derivative. Now, the partial derivative is useful for defining another important concept that we're going to be using a lot, which is called the gradient. The gradient can be thought of another way of extending the derivative to multivariate functions. So the gradient of the function of a multivariate function f with respect to its parameters theta and evaluated at a point theta 0 is given by is as follows, and this is a vector. This is a d-dimensional vector whose components are the partial derivatives of the function with respect to each of its input. So here, the second component of this vector is the partial derivative of f with respect to its second input, theta 2. I am going to give an intuition for what the gradient is and why it's important using a few examples. And I encourage you to review again material from calculus if you are interested in a more formal definition of how of what is the gradient and various properties of the gradient. In order to give you an example of a gradient, we need a multivariate function. And for this, I'm going to define a two-dimensional extension of our quadratic function that we saw earlier. So here, this is a two-dimensional quadratic function, and it's a function of two inputs, theta 0 and theta 1. These are each scalar, and so the input to quadratic function 2D is two-dimensional. And these are, here I'm mentioning a few technicalities about the implementation of this function, but the key line that you need to look at is this one, where I'm defining what the function is. And essentially, I'm taking each of these two parameters, I am applying an affine transformation, and then I'm taking the result to the power 2. So this expression here involves theta 1 to the power 2, theta 0 to the power 2, and this is what makes it a two-dimensional quadratic function. We can visualize this function as follows using the concept of a level curve. So here I have a two-dimensional plot, and the x and y axes here correspond to our two variables of theta 0 and theta 1. So for each combination of x and y, or in other words, for each combination of theta 0 and theta 1, I can go on this plot, and I can see here, for example, at -1 and 2, the value of the function is specified by what's on the plot in this area. And inside this plot, I haven't shown every possible value of that the function can take. I have only shown a small number of values which are defined by these ellipses, and these are called level curves. Essentially, the idea of a level curve is that the function takes the value 4 at all the points along this level curve. So all the combinations of theta 0 and theta 1, which if you draw the line there, this combination of theta 0 and theta 1 falls on this inner ellipse. For all of these combinations of theta 0 and theta 1, the function will take the value 4. And similarly, along this second ellipse, the function takes the value 8, and then 12 and 20 and so forth. So these are called level curves. They are analogous to what one would see on a topological map of an area with mountains or hills or valleys. essentially, if you've ever used the topological map will show lines that on the map are all on the same altitude. So let's say they're all at 1,000 meters, and another line will correspond to all the points that are at 1,100 meters. You can view this plot in the same way, where these different points correspond to the altitude of that point, which is defined by the quadratic function. And so the minimum of the function here is at the middle. At the middle, we're looking at a valley, and as we expand from the valley, the function takes higher and higher values, which are given by this by these curves. And again, each curve shows the set of points that exactly has the value 24 in this example. Again, if you're not familiar with the concept of level curves, I encourage you to look at a second or third year calculus course. Now that we have this visualization of a two-dimensional quadratic function, let's visualize the gradient for this for these functions. Here I am defining the equivalent of a derivative for this two-dimensional quadratic function, which is a gradient. And again, the main line to look at is here. And again, here this is the at each point theta 0 and theta 1, I will have a two-dimensional vector, which along the first dimension will be the partial derivative with respect to theta 0, which is here, and along the second dimension, along the other dimension, it will be the derivative with respect to theta 1. You can see that this is indeed the partial derivative with respect to theta 0 by looking at the original expression. Since this is the partial derivative, we can take theta 1 as a fixed constant, and so this term disappears, and now we're only left with the derivative of this term with respect to theta 0, which corresponds to this number, to this expression here. And now we can visualize the gradient using by combining it with the plot that we just saw earlier. So here I have selected 3 points. They're given by the following arrays. These are the coordinates of the points along each point, the coordinates of each point along theta 0. These are the coordinates of each point along theta 1. And here I'm computing the derivative along each of these points. This is the set of, or I should say the gradient. This is the set of gradients. And here I am visualizing this gradient on this level, on this plot, which contains the level curves. And the 3 points at which I'm computing the gradient are these little blue dots that you should be able to see here. And the gradient is it defines the following arrows that you see here. So technically, these arrows are not exactly the gradient. They're 1 minus the gradient, so they're basically the gradient that was flipped to point in the other direction. The actual gradient would be the same arrow but pointing in this direction. But for us, since we want to minimize this function, I will tell you in a moment why it's interesting to look at this point, to look at minus the gradient. Again, as I said earlier, each gradient is a vector, and since it's a vector, we can visualize it via an arrow. It's a two-dimensional, it's this two-dimensional arrow here, or this arrow in two-dimensional space. And we can immediately make a few observations about these vectors. The first observation is that they are all pointing inwards, closer towards the minimum of the function. Because this is a quadratic function, everything that's going to be inside of this level curve is going to be smaller than, for this one it's 20, and in every case the gradient is pointing towards a direction in which the function becomes smaller. Furthermore, you can even show using simple calculus that this arrow is pointing towards the direction at which the function decreases most steeply at this point. So if you think of this as being a valley, then this arrow is pointing towards the direction where the slope of the valley decreases the fastest. So if you were to drop a ball here, the ball would fall along this line because this is where the pull of gravity would be stronger. And finally, another useful observation is that these arrows are always perpendicular to the level curves on which they sit. Again, this is a basic fact about gradients that you can learn in a second or third year calculus course, but you can see here easily visually that these arrows are pointing towards the inside of each level curve, and they're perpendicular in the sense that if we were to draw the tangent to this level curve here that touches this dot, this tangent would be perpendicular to the vector. So these are a few basic intuitions about gradients, and we are now going to use these intuitions in order to define a really important algorithm in machine learning, which is called gradient descent. Gradient descent is a very common optimization algorithm, perhaps the most common, and it is widely used in all areas of machine learning to solve optimization problems like the one we saw earlier at the very beginning of this video. And the intuition of gradient descent is really simple. If we want to find the minimum of a function, we start at some point in this, at some value that this function can take, and then we repeatedly follow the gradient along the direction which minimizes the value of the function until we reach a minimum. So here in this example, you can see that if we were to start at this point, this arrow, which is 1 minus the gradient, which is minus 1 times the gradient, would be pointing towards the direction at which the function decreases the fastest. And so if we keep following this arrow in this direction, we will be decreasing the function. Then eventually we're going to hit a different point where the value of the function will be smaller. Then we will follow the gradient again, and so forth until we approach the center of this curve, which contains the minimum. Let me give you an example of what this means. But before I give an example, let's just define gradient descent a little bit more formally. Using mathematical notation, gradient descent is essentially applying the following rule many times for some number of iterations, which are indexed here by the variable I. So we start at some initial guess that it's theta 0 of the parameters, and we repeatedly apply this rule, where here we take the gradient and we scale it by a step size alpha, which is how far along this direction we want to go, and then we combine this term with our current estimate of the parameters to obtain a new set of parameters to which we move from our previous point. If I were to define this in pseudocode, it would look something like this. We start with an initial guess for what theta is, and then we keep performing this update rule, which you see here, and we keep applying this rule until we are at a point where the function is no longer decreasing, which is this thing here. So essentially, until the change between two consecutive iterations is sufficiently small, we keep applying this rule, which again is an analog of this rule. We take the previous value of, we take the previous value of theta, and we take the gradient, we multiply it by the step size along which is the distance that we want to take, and we keep repeating this process. Here I define this algorithm in pseudocode, but it's just as easy to implement it in NumPy. In fact, it's almost exactly as it looked like in the previous slide. Here I have defined a few parameters such as the convergence threshold and the step size, and I've initialized the values of theta to a certain value. And again, while the function is still converging, I keep repeating this rule that you saw in the previous slide. This line is exactly the same as in pseudocode, and the only additional lines that I added here are these two, in which I'm storing the points and the gradients that you see here, and that we visit as we search for the minimum of this function. Now, in order to get a real intuition about this, let's look at the result of applying this algorithm. So here, in the earlier slides, I have pre-computed an optimization process, and now I'm visualizing it. So I initially started at this point here, which is somewhere around minus 2 and 3, and this is one of the points that we had in our earlier slide. And you can see here the gradient at this point. And now I am repeatedly, or starting at this point, I have computed this vector, which is 1 minus the gradient, and then I have taken a certain step along this direction, which brings me to this point here. Now that I'm at this point, I again compute the direction of steepest descent, which is obtained directly from the gradient, and I take a step in this direction. I am here, then I take another step, another step, another step, another step, until I reach somewhere that's really close to the minimum of the function. So this is a visual example of the trajectory that a gradient descent algorithm would take. And as you can see here, it does indeed get us closer to the minimum. You can also play with this code to see the values, to see the results of changing the different parameters of this algorithm. Here I can change the step size from 2 times 10 to the minus 1 to 10 to the minus 1. I just reran this algorithm, and now if I go back here and I visualize it, I obtain a different trajectory. You can see that now I have many more points. We are still taking the same trajectory, but we're taking more steps to reach it, because at each step I'm making a little bit more, I'm making less progress than I used to. We can make this even a little bit more extreme and make the step size 10 to the power minus 2. And now if I again revisualize the trajectory, I get a very, 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 very slow movement. In fact, at the end, it becomes so slow that it doesn't even reach the minimum. So this is this shows the effect of using a learning rate that might be a little bit too small. I can also increase the learning rate. I can make it something bigger. Perhaps I will make it 3 times 10 to the minus 1. Now I just reran this algorithm. I can revisualize this, and now you can see the trajectory. Here we're taking a much bigger step. We slightly overshoot. We end up here, then we take this trajectory, but it still brings us closer to our final point. I can keep doing this. I can further increase the gradient, and I can revisualize this. And now you see that we are overshooting even more. We're going here, 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 and now our trajectory becomes a little bit chaotic, and in a sense we're slightly wasting movement because each step is too large and we're overstepping a little bit. To make it a little bit more, even a little bit more extreme, I can increase the gradient size, the step size even more, which makes the algorithm not even converge, because at every time step here, at every step I'm overshooting the value of this. I'm basically jumping all the way across this this region where the minimum is, and I'm going to the other side, and I'm just stepping back and forth, and we're not really converging. So this is what it looks like when your step size is too large. And again, if we set this to something more reasonable, we have a better trajectory. And finally, the outcome of using a smaller convergence threshold is that we are going to be taking a little bit more steps here that are small, and we are reaching closer to the minimum. So hopefully this definition of gradient descent will hopefully you understand it at an intuitive level, and I encourage you to play with this code on your own and again get a better intuitive feeling for what gradient descent does and how it works. Now, in the rest of this lecture, we are going to use gradient descent and apply it to the kinds of models that we saw earlier to obtain our first supervised learning algorithm.